interesting thing. So all of these surveys are actually to be STEM for polarization. But they have not thought about, I mean, the main idea is polarization. This is like you can do, I mean, so when I showed it to Lavin, he said, no, like, you sort of doing.
I'm happy to field any these good questions, but maybe we should.
Okay. Okay, thank you. I'm going to talk about some simulation work I've been doing with my postdoc Short and student Alan Young. And this all really started off, I've been thinking back, I think in probably 1989 when I was here, and started up a collaboration with Hugh Kaufman, and we decided to simulate clusters of galaxies, and we were really proud of what we managed to do. We took an immense supercomputer, silicon graphics workstations, which had just newly arrived at CITA, and when they weren't being used for flight simulation, they were usually pretty early in the morning. We did this huge box and we put 32,768 particles in it and managed to do a simulation of a cluster of galaxies. Didn't actually get around to publishing it until 1992. But here's a picture of that. So this is the cluster of galaxies, one of the first simulations. And one of the things we were interested in was how clusters evolve over time. This is just a picture of how the entropy within that cluster changed. The outer radius grows with time and the inner builds up through gravitational shocking. So these were very simple simulations, but they were sort of, just starting the whole thing off. And I looked at the paper and saw the sort of things we said we needed to do was that we needed to explore a whole range of different cosmologies. Well, we don't really need to do that anymore because cosmology now mostly sorted out. But we needed a whole range of different initial conditions as well. And we now get around that by having large boxes with the correct type of fields in. And of course we needed more particles to better resolve the clusters, and we wanted to do a range of different cluster physics. So I'm going to talk now about the simulations we're doing at the current day. So we've got a project going to simulate the clusters within the Millennium simulation volume, so a 500 megaparsec cube box. And the idea is to do all the clusters in that box and work out the physics so we get a completely representative sample of clusters to compare with the real world. So we're using the same cosmology. It's not the most up-to-date cosmology, but it matches that of the Millennium simulation. And we've got various different gas simulations with gravitational heating only. We've got one with uniform preheating at Z equals 4. And they've been run on the whole box, so we've got thousands of clusters simulating those. They were done actually quite some while ago, and it's taken us a little while to come up with a model with a realistic feedback scheme in. So we've had feedback simulations done in smaller boxes which work quite well, because whenever we went to the really large box and looked at really big clusters, we never actually got galaxy properties which seem to be very realistic. So recently we've looked at it from the other point of view. So we've decided that we're going to force the galaxy properties in the simulation to be realistic. So we're starting off with a semi-analytic model, the Unix semi-analytic model, which produces a good galaxy population, correct luminosity function, correct black hole masses. And so we know that what we're ending up with in terms of the sources for our feedback is realistic. So this is the idea behind the simulations then. We take the Millennium simulation itself, dark matter only, relatively high resolution, and we construct merge trees from that, and we run our semi-analytic model. So we have a model here with stellar and AGN feedback, and then we use this as a source of heating for our hydro simulation. So we run a hydro simulation, but put in the heating that's coming from the semi-analytic model. So the advantages of this method are that the feedback is coming from a realistic population of galaxies. It includes both stellar and AGN feedback. And it's actually got a higher mass resolution than the other ones that we've done. The disadvantages are that you can't put radiative cooling in a self-consistent way, because the feedback is not directly coupled to the radiative cooling. So for that reason, we're not able to reproduce full core clusters with these simulations currently. And then we have to do this with resimulation. We can't apply it to the whole Millennium simulation all at once. But we do resimulate all the high mass clusters. So we have 200 clusters with temperatures above 3 keV. So a good sample of that. So this is just showing you the cluster numbers that we've got. So even back at redshift of 1, we're managing to resimulate of order 100 massive clusters. Here's the feedback model then that comes from the L Galaxy scheme that originates in Munich. So for supernova feedback, we've got energy available from the supernovae, but actually a lot of that energy is used to heat up cold disk gas. So in order to prevent excessive star formation, the supernovae are constantly having to reheat the disk gas and prevent it from forming stars. And so this is actually a significant fraction of the total energy that's available being wasted in that way. When it comes to the feedback from black holes, this scheme here does have black holes in it, but it doesn't couple those to the intracluster medium because it's not interested in that. And so in order to do that, we use the scheme that Richard Bowers proposed, where basically we treat the black holes as having accretion in two varieties. At very high accretion rates, you've got a thin disk, it's very radiatively efficient, and this is the quasar mode, and so there's very little energy available to couple into the intracluster medium. And so the efficiency of heating is quite low, only 2% of the Eddington rate. But then at very low accretion rates, as in the universe around us today mostly, you've got radio low accretion, which is much more efficient. So essentially we take the black hole growth and we take the energy input to be proportional to the rate of increase of mass of the black hole in this one. Okay, you only put in the supernova heating. Previously we've done simulations where we only put in supernova heating and actually successfully reproduced the properties of groups. But actually this is at the expense of having a huge star formation rate and actually very efficient very efficient supernova feedback with efficiency parameters of 1, or in some cases more than 1. If you actually do it more realistically in this model, so a lot of the energy, as I said, is wasted heating up coal gas, and it actually has many fewer stars in our previous simulations because all galaxy formation is highly suppressed. But actually, it's feeble if you just put in supernova energy. So you have to include the AGN feedback, and when you do that, you get a satisfactory reproduction of the L2 relation. Okay, this plot is just to show you the range of masses that we have for the clusters. So the green points here are all the clusters in the Millennium simulation reproduced in the preheating run. And then the red points are the ones that we did with this realistic feedback model. So we did all the high mass ones and a selection of the low mass. These are the entropy profiles of clusters. So this is here what you get just from gravitational only heating, and these bands here represent observations of real clusters. And then this is what you get with our feedback models. Now you can see that observation clusters are split into these two kinds that we've heard about. There are the cool core clusters, which actually have very cold gas in their centers, and the non-cool core clusters, which are being heated up and have a higher entropy. Okay, so we don't actually do too well in the middle here. That's just showing you the entropy at R500, which is a lot better. I'll skip on. I just wanted to concentrate on telling you a little bit about the baryon fractions. So Steve Allen's was the first one to really try and use the baryon fraction to do cosmology. And he looked at very bright, cool core clusters and measured the baryon fraction as a function of radius and showed that it converged quite rapidly to a sort of roughly constant level that you could then use to try to do cosmology. So you look back to higher redshift and say, what cosmological model can reproduce this? This is what we get from the simulations, and it's hopeless. It doesn't match at all. Okay? Why not? The reason is that we don't reproduce cool core clusters because we don't have the radius of cooling in the middle. However, this is what you get if you look at the excess sample, a representative selection of clusters going out to larger distances from the cluster core. So this is now going out to R500, and these black, solid black lines here are non-cool core clusters. And the cool core clusters here all have much more gas in the core. But actually, if you concentrate on the non-cool core clusters, which actually make up the majority of clusters in the representative sample, we actually do pretty well at reproducing the baryon profiles. And both of these essentially agree by the time you get out to R500. Okay, so here's two different, completely different kinds of heating model. Preheating and feedback, and these are the baryon fractions they predict at R500. This is just gravitational only heating. These are the observations, and they're sort of a bit of a mess, but they do show. Look in here, right? There's a band of observations down here, which is doing pretty well. We're slightly above it because we use slightly too high a gas fraction, probably, in the Millennium simulation, so we can pull that down a little bit. It's not a bad fit. Okay, I want to talk about evolution of the baryon fraction. So you've got two completely different physical models. 2 minutes, that's all I need. And they evolve in very different ways. So in the preheating model, what you're doing is at an early time, you're raising the entropy of the gas and expelling it from the cluster. And so at early times, here, the gas fraction is very low. So this is looking at the most massive clusters in the simulation as a function of redshift. And as you move towards the present time, essentially, they move back towards a situation you would have had if you didn't heat them up. So there's a very strong evolution in the gas fraction. If you look at a model with continual feedback from star formation and AGN, then actually it's almost self-similar. Okay, so the feedback's continually injected and it maintains a sort of steady state. So by the time you get back to a redshift of 1, these two models have very different predictions. Okay, well there is observations of baryon fractions in clusters, which do go out to a redshift of 1. So this is data from Horn et al., just looking at every cluster that's been observed with Chandra and measuring its baryon fraction for those where we can go out to R500. And this is the ratio of the measured baryon fraction to that predicted in the pre-heating model. 1 if the model is correct. And you can see it's not. However, if you take your feedback model, you have a ratio which is approximately constant. This slight offset from 1 is again, as I said, probably because we've used slightly too high a mean gas fraction in the simulation. So I think that's perfectly consistent with the data. And so the conclusion is that for the first time, really, we're able to say that we strongly favour a realistic feedback model over one which has an early preheating.
So, really nice. Now we lower sigma 8.8. What changes do you think might happen?
I don't think that it would change this general conclusion here, which is just basically, I mean, the main conclusion here is just based on when you heat the gas in these clusters. So it would change the overall number of clusters as we have to change this conclusion.
The relationship of mass,
Yeah,
but you don't think that's the big issue. I mean, that is not.
for that conclusion, it's not going to make any difference.
Have you just taken some of the things for fun? What would it seem to me?
We haven't done that yet. But tell Carlos that we should run it. We should rerun with Lois.
Simon,
Oh, Simon, you're in the audience. Hi.
you know, you put me scared.
Yeah, not really yet.
Do we have a resolution?
I'll go as fast as I can. Despite my heritage, or starting my career as Carlos Frank's grad student, I have to say up front, I have never simulated a cluster of galaxies. I stubbornly refuse. So he's still giving me the evil eye. Yes, so do you. So I'm going to be talking this morning about a survey that I did to find and study clusters of galaxies, primarily above redshift 1. These are the names of all the people who are involved with the survey. And our team of about 30 people are a disproportionately large number of Canadians or adopted Canadians, and 3 citizens, myself, Hank, and Suba. The current generation of Z greater than 1 cluster surveys fall in, there are really 3 methods basically. They fall into 3 types. Those that use infrared selection, those that use the Sun-Zeldovich technique, and those that look for hot gas emission from the potential well, look for X-rays. The ones you see there in yellow are ongoing or completed surveys, and this is not by any means a complete list. And the ones in orange are planned or proposed, so they're coming. Now, our survey uses an infrared adaptation of the efficient 2-filter red sequence technique, which Howard Lee and Mike Ladder's pioneered, hence our name, the Spitzer adaptation of the red sequence cluster survey. So, to apply the technique, you need observations in 2 pass bands, one each side of the rest frame 4,000 angstrom break. At redshift 1, the rest frame break passes into the IR. So if you want to look for clusters above redshift 1 using the red sequence and do it efficiently, you need to have some kind of infrared observations. And we use the 3.6 micron channel on Spitzer IRAC as our red pass band. So we got those observations for free. Spitzer, the widest field Spitzer legacy survey is Swire, and those observations were taken for us. but we had to go out and get our own blue band observations, and we chose to do this in the Z passband, short one of the rest frame 4,000 angstrom break. It took us quite a while to get these. It took us 25 nights over 3 years to cover the full 50 square degrees of this wire survey. We finished getting those observations in late 2008. We processed all the data, and we have about 200 new cluster candidates above redshift 1. And as I'll show you in a minute, the Z minus 3.6 color gives you actually a pretty good estimate of the redshift. And that photo Z gives you a pretty good estimate of the redshift of all of those clusters. The survey summarized in these 2 papers by myself and Adam Muzzin. There are 6 sparks fields. 4 are in the north, and we got our Z-band observations for those from CFHT, so a big thank you to Cantac for giving us the time supporting this project. And 2 of the fields are in the south. We got the observations for those fields from CTIO. The white rectangles you see there are the footprints of the optical pointings on top of the Spitzer IRAC data. And when all was said and done, the total usable area of the survey is about 42 square degrees. In the next few slides, I'm going to show you some clusters, some confirmed clusters from our catalog. Remember I said we had about 200 candidates. We've been spending our time in the last couple of years going out and confirming some of these candidates. Now I know redshift 0.87 is less than redshift 1, but this cluster was just so rich that we couldn't resist. And we went and got some data from Peck, and we confirmed this cluster. It's as you can see, it's very rich. It has an estimated preliminary velocity dispersion is based on 16 members of about 1,200 kilometers a second, so the order of MS 1054, and a mass of about 2 times 10 to the 15 solar masses. This analysis was led by my then postdoc Ricardo De Marco, who's now faculty at the University of Concepcion in Chile. There's another confirmed cluster. This one is at redshift 1.16. Has a preliminary velocity dispersion of 950 and a mass of about 8 times 10 to the 14 solar masses. Now, those were observations taken at Keck. We've also been following up clusters at Gemini, and I'll have quite a bit to say more about that in the next couple of slides from now. But this is a confirmed cluster at redshift 1.18, and if you look at the shape of this cluster, you can see that they're these redshifts, they're very clearly not nice, circularly symmetric, happy, relaxed clusters.
How big is the masses?
Just from the velocity dispersions. So far, we're going to do it some other ways as well. I'll talk about that. So this one, I mean, it's clearly more filamentary. This one is redshift 1.20. We've got, in this paper, we have 28 members. And finally, this is a cluster. This is the highest redshift cluster that we've confirmed yet from the survey. This is clearly a rich cluster. These green things are foreground stars. This has a preliminary velocity dispersion of about 1,000 kilometers per second and a mass of 9 times 10 to the 14 solar masses. And it may be that this turns out to be the most massive cluster we have above redshift 1. So, because of the sheer volume of the SPARCS survey, we're able to find a large number of these rare, rich clusters, which are the likely progenitors of the clusters that have been studied previously at redshift less than 1. So we'll be able to do all sorts of wonderful galaxy evolution studies as a function of environment, I hope. But you know, we're all playing the cosmology game, so we like to see if we can do anything with 50 square degrees above redshift 1. At lower redshift, the RCS and the Sloan surveys have measured constraints on omega m and sigma 8 from the evolution of the cluster mass function. To do this efficiently, the survey data itself is used not only to detect the clusters, but also to estimate their redshifts from the red sequence color and their masses from the optical richness. So the question is, can we estimate cluster redshift and mass from just from the catalog at redshifts greater than 1? And our work is preliminary, but it looks like yes, we can. Here is a plot of Z minus 3.6 color versus spectroscopic redshift for 6 clusters. The 5 I just showed you and another one that we've confirmed at redshift 1.21. And it depends a little bit on what formation model you choose, but you can see that the agreement is generally pretty good between the predicted Roosevelt and Charlotte color, these different lines here, and the spectroscopic redshift. So it's looking like that when you detect a cluster, you can, in fact, infer its redshift accurately just from that Z minus 2.6 color. This plot shows the same 6 clusters, but what we've plotted here is the mass estimated from the richness versus the mass estimated from the velocity dispersion. And again, the uncertainties are large, but the agreement is decent. So it's looking like, just from the richness of the cluster, you can make a pretty good estimate of its mass. Its optical richness, you can just make a pretty good estimate of its mass. I'm going to talk a little more about this survey that we're carrying out on the next slide. We have a survey that's almost completed, which is going to measure 50 spectroscopic redshifts in each of 10 rich sparks clusters with a median redshift of about 1.1. So very soon we'll have 10 plots. We'll have 10 points on this plot, and we'll have quite a bit smaller uncertainties on this plot and on the previous one. So I think it's fair to say at this point this work is still preliminary, but the prospects are looking good, not just for sparks, but for the entire current generation of cluster surveys, which are aiming to estimate redshifts and masses above redshift 1 directly from optical infrared imaging. Okay, on to G-class. Now, G-class is a really huge undertaking. At its core is 220 hours with the GMOS North and South instruments over 6 semesters on Gemini. And to put that in context, the GDDS survey was about 100 hours. Half the time is coming from the US, and half the time is coming from Canada. So again, a big thank you to Cantac for supporting this. And our goal is to measure 50 spectroscopic redshifts in each of 10 rich clusters in this redshift range between 0.87 and 1.34. We're well on track to do this. If we get our current time request, our time request is in at the moment for 2010B, then we will be done by the end of the year. We have quite a bit of supporting imaging data. We actually have 12 passbands for these 10 clusters. Optical, near IR, and deeper follow-up Spitzer. And we're chugging our way through, we're getting X-ray follow-up. And we have an HSD proposal in also to get HSD. Now we can do clearly many projects with this data set, but broadly we're hoping to do, we can do cluster galaxy evolution, cluster dynamics, and we can calibrate the cluster mass richness relation at redshift 1, which has not been done before, and we'll definitely need if we're going to put in, if we're going to constrain any cosmological parameters or play any cosmological games with this data. Now, the reason we went for Gemini is because it's a technical reason to go for Gemini. The GMOS instruments are cleverly designed, and they have this really nice option where you can do sky subtraction using a technique called band shuffle. The problem when you want to get spectroscopic follow-up of clusters is that you have many nice juicy targets, but they're all in a very tiny area of the sky. It's just very difficult to get slits down on the targets that you would like to get the slits down on. And with using this band shuffle technique, you can shrink the width of your slits quite dramatically to about a third of the width of a conventional spectrograph like Elris on Keck, and you can just see here for this cluster. These are both examples of mask that we use, and you can see here there are 52 slits on the GMOS mask, and 12 slits on the LRIS mast. So, all things being considered, we're getting about a factor of 4 more efficiency with Gemini than we could get with Keck, and that's why we did our follow-up with Gemini. So this is a hot off-the-press plot. They're actually, so what you see here is a stacked spectrum for each of our 10 clusters going from redshift 1.87 to redshift 1.34. There are actually 360 galaxies have gone into making this plot. Here we've stacked 45 members in this cluster, 48 members in this cluster, and actually 79 in the green spectrum. And when you have so many members, you can really beat down your noise, and you can actually see some features of what's going on in these clusters. And the obvious thing to look at is O2, measure how active the galaxies are, how much star formation is going on. And interestingly, we do not see a monotonic increase in the strength of the O2 line with redshift. These clusters are all over the place. And the O2 line varies quite a bit. You can't see it from this plot, but it's not a function of mass either. We have some of our more massive clusters have a lot of O2. So we're just starting to tease the details out of this data set, but look out for a slew of papers over the next few months as we start to figure out what we actually have in this sample. So I told you the highest redshift cluster candidate we've confirmed at the moment is redshift 1.34. It turns out that using this Z-2.6 red sequence method, we actually detected fewer cluster candidates at redshift 1.4 than we expected, and I don't think it's anything to do with the universe. It just turns out that the Brunswick and Charlotte model predictions and the observations are in good agreement out to 1.2, but the disagreement grows with increasing redshift. So I don't think we quite understand how galaxies are evolving above redshift 1.2. Turns out that early type galaxies are about a half a magnitude fainter at redshift 1.5 than our pre-survey models predicted, making quite reasonable assumptions. So what this brings us to is that L-star galaxies are only marginally detected at the limiting magnitude of the survey. So we need a new method, unfortunately, to detect clusters above redshift 1.5. And we have one, we call it the stellar bump sequence. And I'm running out of time, so I can't really have details to go through. I don't have time to go through the details of exactly how that method works. But we have a method. And what we do is we divide up our catalog by color and clusters, but this time using 3.6 minus 4.5 color. And again, we play this same game. We can detect our clusters as peaks in the galaxy density maps once we do that. And just as a sanity check, the clusters that we confirmed earlier also show not a red sequence bump, but what we call a stellar bump, 3.6 minus 4.5 micron stellar bump, which is all good, and it should be. But the whole point of doing this was to find some higher redshift candidates, and we do find some higher redshift candidates. You notice that the stellar bump sequence is a little bit redder for these candidates than it was for the two I just showed you, so we're pretty confident they're at higher redshift. They have photometric estimates of 1.5, 1.6, and 1.5. So we applied to follow these things up. We have time coming up on VLT, and we have applications in to follow up more candidates next semester with VLT and with Keck. So fingers crossed, in the next few months, we'll actually confirm some Sparks candidates at even higher rate. Thanks.
Looks like a very nice project. I thought the GMO spectra is actually particularly impressive. So in the individual spectra, I'm sure you can't see the absorption features, but you can probably see the oxygen emission line. So is the reason why there's no correlation between the oxygen line strength and the break strength because a lot of the line is coming from just one or two objects?
Well, we're teasing that out, but that is a possibility. If you just have some bright things, then that could dominate your spectra. So, you know, these are literally spectra we've been getting in the last couple of months. So we've got to go through and really understand that. And I don't want to say anything beyond that, but definitely it'll be fun to do it.
This part is very good.